before spring break. I had the flu, so I missed Thursday. So it's been a while since we met. I put the Unit 12 exam online, so it's under Canvas. And I made it where you could submit it online as well. So, let's see. So I put the PowerPoint for Unit 13 and 19 under announcements. Your next test will be off of 13 and 19. And then under assignments, you have your Unit 12 exam here. And then I put a bubble sheet with it. So whether you give it to me in person or if you submit it online, I want you to put it on the bubble sheet. So make sure you do transfer to this. And then what you could do is you could just take a picture of the bubble sheet and then just re-upload it on the assignment here. Probably the easiest way, or it's a PDF. I mean, you could fill it out, resubmit the PDF file, whatever's clever. Or if you want to give me the bubble sheet in person, that works too. And then when we get to the true and false, you got like 5 of them, 5 or 6. True is A, B is false. So do the true and false on the bubble sheet as well. And then you just have 2 short answer questions. Can you guys hear the audio okay? There was a question in the chat.
Yeah, good.
All right.
How are you feeling?
I'm better. I was sick for like 5 days, man. It was even a couple days of spring break. So I got
Not a joke.
it wasn't COVID because I did a COVID test. It was just some sort of flu bug I got. But thanks for asking. Feeling great
Nice
now.
to having you.
Huh?
Nice to having you back.
Oh, thank you. All right. Oops, wrong one. All right, so 13 and 19, we're finally going to start talking about the parts that we're using in shop. More on unit 19 than 13, but 13 has some good basic principles in this section. So after studying this unit, you should be able to define bimetal, make general comparisons between different bimetal applications. We'll take a look at the rod and tube type of bimetal. We'll look at fluid-filled controls. You still see these a lot, the fluid-filled controls. So you'll definitely still be working with them. Bimetal still used all over.
Are you sharing a PowerPoint?
Uh-oh, it's not sharing. Thank you. That's one thing. Zoom is lying to me tonight. It says I'm sharing when I'm not. So if it doesn't look like I'm sharing, please speak up. Thanks, Bo, for that. All right, so the fluid fill controls, these are still used a lot. Same with the bimetal. You're seeing bimetal even in your other class with the little bimetal overloads that they're putting on the equipment. So a lot of you are in that 122 course, and you guys are seeing these little bimetal overloads right here mounted on the compressor. So you're gonna, and they're gonna use this technology for quite a while. It's reliable. It's very simple. There's not many moving parts on it. So I could see them using bimetal for a number of years to come.
But it's like an external
Yep.
thermostat, right?
You got it. So these, whoops, wrong one. Those ones there, those are all external overloads. So these would be mounted on the side of the compressor. And then if it was internal, they still use bimetal quite often. Sometimes it's a thermistor embedded in the motor winding. Other times it's internal bimetal. Let's see, three-phase. Starters. There we go. So on a three-phase motor, if a lot of times if it's in an internal overload, they'll use a Y-type motor. And the overload will be right in the middle. So like on here, that little internal overload in the middle, that'd be a bimetal internal overload. And then same thing when it warped, it would break the path between your line 1, your line 2, and your line 3 on that three-phase motor. Downfall of the internal one is we can't change it. We have to change the whole motor. And then if it's external, that's really easy to change. This is a good little manual right here on motors. So I'm going to put it in the chat. If you guys want some additional reading material, this would be a good little packet to look at here. This even shows an internal overload on single phase. So this is a good diagram right here for a single phase motor with an internal overload. And that little internal overload is bimetal on this one as well. So under the fluid filled controls, we have a partial liquid and a partial vapor filled control. Most all of them are partially filled. They're not 100% filled with liquid. If they filled it 100% full of liquid, you don't have much room on there for expansion before something's going to give. Where if they put some vapor in the control, we have more room for liquid expansion inside of that control. So most of them are partially filled with liquid and vapor, not fully filled with liquid. We'll distinguish between the bellows, the diaphragm, and the bourdon tube. We'll look at how a thermocouple functions, and we'll look at a thermistor. So types of controls, we could have electrical controls, types of automatic controls. We could have electrical, these control electrical devices. You could have mechanical controls. These are used to control fluid flow. So this would be strictly mechanical. It would not be on a wiring diagram at all. So in your one 22 course, your TXV is a fully mechanical control. So that TXV valve, it's going to modulate how much refrigerant flows into the evaporator based on the temperature of your suction line. And this mechanical control does have a diaphragm built into the power head. So in your sensing bulb here, it's filled with refrigerant. As your suction line gets warm, you're going to heat up the sensing bulb. The pressure is going to go up in the sensing bulb. That's going to cause the diaphragm to warp downwards. That will push down on this needle, which pushes down on this seat. And that's going to allow more fluid flow to flow into the evaporator. So we're going to get more refrigerant in our evaporator when the suction line is warm. And then all of a sudden, if your suction line started getting cold, the temperature of the sensing bulb is going to go down. The pressure in the sensing bulb goes down. Spring pressure and suction pressure start to overcome diaphragm pressure, and they push that diaphragm back upwards a little bit. When this seat moves upwards a little bit, it's going to close off the flow going into your evaporator. So when you heat up the sensing bulb, we have more refrigerant flow into the evaporator. You cool off the sensing bulb, we're going to have less refrigerant flow into the evaporator. So this is a mechanical control that is modulating how much freon or refrigerant is going into the evaporator. So it's not a start-stop device. It's modulating that fluid flow. And then you're going to have quite a few other controls that are strictly mechanical. So you have what they call an EPR valve, an evaporator pressure regulator. When you look at this, there's no wiring on this. This is a mechanical control. And then the CPR valve looks just like the EPR valve. This is strictly mechanical. And it's modulating fluid flow. Same thing when you get to the headmaster. This is this bulb on the headmaster. This is filled with refrigerant. And this also will vary the amount of refrigerant flowing through the condenser there. So all four of those valves, the TXV, the CPR, the EPR, and your headmaster, they're all controlling something. And they're strictly mechanical, so they're not going to be on a wiring diagram. Electromechanical, this is going to provide electrical functions or control fluid flow. So like a solenoid valve is an electromechanical part. Those relays and contactors you guys are using, those are electromechanical. When you power up the coil, it's going to pull down on a little plunger, and then it's going to close some contacts and it's going to open some contacts. So the electrical side is us creating electromagnetism. The mechanical side is that plunger being pulled into the valve. So even though it's electrical, there is a mechanical action within that relay and within that contact. Your gas valve is also considered electromechanical. If you have a solenoid valve, that is electromechanical. So on a solenoid valve, this could be on a water line, could be on a drain line, could be on the hot gas line, could be on the liquid line. So on this one here, right now, they got the valve closed. And then when we power up this coil, we'll generate a magnetic field or electromagnetism in this coil. And that electromagnetism is going to pull this plunger up. When it pulls that plunger up, that's going to allow fluid to flow through that solenoid valve. So you have an electrical action, you powering up the coil, creating electromagnetism, and then you have a mechanical action where the valve is actually opening up. So the valve could fail mechanically, or it could fail electrically. Same thing on your gas valve. When you get 24 volts to the gas valve should open. So right now they're showing the gas valve with the coil on it de-energized. So the coil's up here. And while it's de-energized, it's not pulling up on this little arm. So right now we have gas coming into the gas valve. Gas is going to go up on top of this diaphragm, and gas is going below the diaphragm. So if I have 3.5 inches of water column pressure on top of the diaphragm and below the diaphragm, that diaphragm is going to stay in the same position. It's not going to allow the gas to flow out to the burners. So it's not going to allow the gas to come out to the burner if I have pressure on top of the diaphragm and below the diaphragm. Now, when we power up the coil, now it pulled this little arm up. When it pulled the arm up, it shut off this little port that allowed the gas to come up on top of the diaphragm. And then there's a little bleeder up here that bled off that gas to the pilot. If not, there'll be a little small vent on the side to purge that gas off. It's just a small amount of gas there. Once that gas is purged off, now there's only atmospheric pressure up here on top of the diaphragm. And now you have your 3.5 inches of water column below the diaphragm. Now that gas pressure is going to push up on the diaphragm, and that's going to allow gas to go out to the burner. The minute you de-energize that coil on here, we're going to lose the magnetism. The spring's going to push this lever back to where it's going to tilt back in the opposite direction to where it allows gas to go on top of the diaphragm. So the minute we de-energize it, we're right back to this position where the valve is closed. So we have a mechanical action inside of that valve, and we have electrical going to it. So this is an electromechanical part here. And they're not bad to troubleshoot. You know, you want to make sure that you have gas pressure coming into the gas valve. So we can measure that with a manometer. And then you want to make sure you're getting 24 volts to the gas valve. And then you should be getting pressure out of the gas valve the minute you get 24 to it. So if you got gas pressure going into the valve, you got your 24 volts, but you have no pressure coming out of the valve, now you got a bad valve. But if you go to troubleshoot it and you have pressure coming in, nothing going out, and no voltage to the coil, well, don't assume it's a bad valve yet. The problem is we don't have voltage to the coil on that gas valve. So the only way it's going to work is if there's gas present on the valve and you're sending 24 volts to the coil of that valve. Questions on the electromechanical valve? So you'll break down the parts of this gas valve a lot better in your 131 course. We'll talk about like the sequence of operation in this course, but you'll talk about the different types of gas valves when you get to the 131 course. So you'll talk about like the smart valves, the ones that are heater operated, so they're slow to open, slow to close. Then you'll talk about the diaphragm type valve like this one here. All right, so your contactor, your relay, the gas valve, those are all electromechanical. And then we have electronic controls and devices. These have circuit boards on them. They could be at 5 volts DC. They could be at 24 volts AC. They could be at 120 volts. Basically anything with a circuit board on there, you can consider that an electronic component there. And we do troubleshoot a lot with circuit boards. So like your gas furnace, everything in the furnace is ran off of that circuit board. So that circuit board on here is the main brains behind this furnace. A couple of you guys are working in the field right now. It may be at an apartment, or some of you guys are doing service work. But with a furnace, if you guys have worked on a furnace, you notice not everything comes on at once. Like with a heat pump, when you call for heating, your compressor comes on, your outdoor fan comes on, your indoor fan comes on. Basically, it's all coming on at once. That's not the case with the furnace. That circuit board is controlling the sequence of operation. So on a gas furnace, the first thing we're going to do is call for heat on your thermostat. The next thing that's going to happen is this combustion motor, number 4 here, is going to come on. What that does is it's going to pull air through the burners. Make sure I'm sharing. It's going to pull air through the burners, through the heat exchanger, and then make sure we have a good draw going up the flue pipe. So after we call for heat, first thing that comes on is your inducer / combustion motor. The furnace has to make sure that this motor came on. So what it did is it wired in a pressure switch next to it. And that pressure switch has a tube that's going over to where this inducer motor is. And it's looking that it created a vacuum in this heat exchanger. So it created a negative pressure in that heat exchanger. If your pressure switch doesn't close, your furnace will not ignite. After your pressure switch closes, then your igniter is going to be energized. So it doesn't matter if you have a hot surface igniter or if you have a spark igniter, your igniter is going to be energized. After your igniter, you're going to energize your gas valve, which is right over here. After your gas valve is energized, we have to prove the flame was lit. So you have a flame sensor. And then the last thing to come on is going to be the blower motor. All of that is controlled by the circuit board. So once you call for heat, the inducer motor comes on, creates a negative draw through the heat exchanger. The pressure switch proved the inducer motor was on. Then the igniter is going to start glowing. Once the igniter is glowing, then we energize the gas valve. Once the flame lights, we have to prove to the furnace the flame lit using a flame rectification sensor. And then the last thing to come on is going to be the blower motor. So when it comes to the digital controls or our electronics, you need to know all the inputs and outputs on these devices. So on these circuit boards, you have these wiring harnesses, and you need to know the sequence of operation. You need to know those steps in order to troubleshoot this. And looking at the wiring diagram, you'll be able to figure out what's an input into that board and what's an output on that board. And then you have to look to see where the furnace failed, and that's where you're going to start troubleshooting. So if you call for heat and nothing comes on, you're not going to jump to the igniter. That's not first. If you call for heat and nothing comes on, you're going to troubleshoot your inducer motor. Why isn't your inducer motor coming on? And then if your inducer motor does come on, you got to troubleshoot whether your pressure switch is closing. So with equipment with a circuit board, you got to know the sequence of operation in order to troubleshoot these boards. Because when you look at a gas furnace wiring diagram, it doesn't tell you this is first, second, third. They don't do that at all. They give you this. And this is like what I would call a schematic. It's in between a ladder and a pictorial. But this will be your diagram for that furnace. So after I call for heat, what is the first thing that comes on again?
Inducer motor.
Good. On this diagram, the inducer motor is right down here. So if we call for heat and the inducer motor does not come on, we need to troubleshoot this motor here. So we would want to see, are we getting 120 volts out to that motor? And it shows you right on the wiring harness here what pins are powering up that motor. So this would be first. The inducer motor has to come on. Next is your pressure switch has to close. So the pressure switch has an orange and a yellow wire going to it. And if we trace it back, it looks like it's off of pin 4 off the wiring harness and pin 3 on the wiring harness. So we're going to want to get in there and see if that switch closed. If you're reading voltage between 3 and 4, if you're reading 24 volts there, that switch did not close. That switch is still open. Because if the switch closed, it'd be the same leg of power and you should read 0 volts. After your pressure switch, the next thing to come on is going to be the hot surface igniter. So you'd have to jump back down to this portion of the board. And then after the igniter comes on, Then we're going to energize the gas valve. This is the gas valve over here. So the gas valve's coming off of pin 2, and it's coming off of pin 8 on the wiring harness. So once your igniter glows for a set amount of time, next thing is you should get 24 volts of the gas valve. Then after your flame lights, after you energize the gas valve, the flame should light. And your flame rectification sensor is going to prove the flame lit. I'm blind right now. Where's my sensor at? Let me right off of this. Where did they put the flame sensor? I'm looking for FS. They got a jumper on here. Hopefully they're not double. Sometimes they'll double up the igniter as a flame sensor, but normally you'll have a separate flame sensor that would say FS for your flame rectification. After your flame sensor proves flame lit, so this one may be doubled up through the igniter, so they got a jumper on the board. The last thing to come on is going to be this blower motor here. So we got a whole sequence of events that has to happen on this furnace. And if it fails at any given point, you got to figure out where it failed. So most of them, no, that one has a jumper too. I just wasn't seeing on the last one. But most all these furnaces have a flame sensor. So you have a separate wire for flame rectification. Same thing on ice machines. There's a whole sequence of operation on the ice machines. They're expensive circuit boards. So when we look at the ice machine, they're not $100 board like a furnace. You know, you look at these, Hoshizaki, almost $400, Scotsman, $500, Manitowoc, $569. These are expensive circuit boards. So you better troubleshoot it right. If not, you're throwing a lot of you're throwing a lot of money at that piece of equipment and it's still not going to work. Go ahead, Jacob. Can you hear me? You're on mute. If you're trying to say something, Jacob, you're on mute. Oh, the microphone is a fuse board person. Yes, you can replace the board by itself. So we just want to accurately troubleshoot it. So there's a lot of time. I used to carry these boards with me. So I'd carry a replacement board for Manitowoc, replacement board for Hoshizaki, and I'd have a couple models worth, because not all of them are using the same circuit board. So yeah, these are parts that we would change on a somewhat regular basis. So, but we want to make sure that we're accurate when we diagnose this board here. Same thing on the furnace too. Really check all your inputs and outputs, because you'd hate to miss something like a pressure switch not closing and then say it's a bad board when really it's a bad pressure switch, because there's a big price difference between a board and a pressure switch. As far as repairing the board, you can like solder the little bus lines on the back. But the problem is we offer a warranty on our repairs. So a lot of times your company will do 3 months or 6 months warranty on that piece of equipment that you fixed. So if you solder the bus line on the back of a board and then it fails within that warranty time, then you're doing that callback for free. And a lot of these companies, they really rely on that ice. Like if it was in and out, in and out needs that ice machine working. They can't have the machines down. So we a lot of times we end up putting in new boards versus trying to fix any of the boards. So I'm not a big fan of changing relays or capacitors or resistors on boards, because if it fails, it's going to be a free callback for that customer. So I'd rather just charge them a little bit more up front, put a replacement board in there, and then when we give them the warranty, I can sleep good at night knowing that that is not going to fail because I did a lousy job soldering the board or I didn't fix the board properly. I've fixed them to get them going. So I've taken a wire and soldered it from point A to point B on the back of a board to complete a bus line. But then I wrote on the paperwork, no warranty. This is a temporary fix. Because what will happen is once you get it running, sometimes they'll call your shop and be like, I don't want the repair now. The machine's working fine. Well, I did a temporary fix. That's why it's working fine. That thing's not going to last very long. That wire could pop off, or it's not as solid as a new board would be. So if I do repair a board, I write all over the paperwork that this is a temporary fix and that we need to replace the part. That way, if they cancel the call, I have documentation that I told you this was a temporary fix, not a long-term fix. Yeah, you're welcome. If you're doing facilities and it's like a school district or something like that, and it's your equipment, by all means, you could try and repair these boards because you're going to be touching that equipment or seeing it on a daily basis. So somewhere like if you're working in facilities, you may want to try and fix it. If you're doing service work, where you're going to give them a warranty and you only show up there when something breaks, then you want to replace the board. Or if you do a temporary fix, just document it. And then pneumatic controls are controls that operate off of air pressure. We have a whole class that covers pneumatics. So when you get to the 141, 142 course, you'll talk a lot about pneumatics. Older buildings used pneumatic controls before they came out with direct digital controls. So before the building management systems came out, a lot of times they were running their HVAC equipment off of air pressure. And you'll cover this a lot, like I said, in the 141, 142 course. Pneumatics was never my strong point. I've worked on a couple pneumatic systems, but my exposure is definitely limited. Chris maybe he's good on pneumatics, and he's the one that teaches that course. Devices that respond to thermal change. So devices such as thermostats that open and close their contacts during the normal operation of a system are referred to as operational controls. Safety devices, on the other hand, are typically normally closed devices that open their contacts only when the device senses system conditions that are outside of the desired or safe operating range. So I know a couple of you guys are working in the field already. Can anyone think of a safety device on a furnace? a safety control on a furnace.
Cut off fuse or maybe cycling thermostat, no?
So yeah, you could have a fusible link. That's a safety device. So the fusible link would actually melt if the furnace got too hot. So this would be near the burner section. And then if the furnace got too hot, this thing melts and then you have to replace it. Like here's a little one from Carrier. Carrier did a weird one. They put it right in series with a wire. So if you see something that looks like a resistor on a wire in a furnace, that's something that when it gets hot, it's going to melt and you cannot reset it. So a fusible link, this would be a safety device on a furnace. The fuse on the circuit board, that's a safety device on the furnace.
Thermocouple.
Thermocouple proves that the flame was lit, so that doubles as a safety device. It's a kind of an operating control and a safety in one. Has anyone ever heard of the term limit switch on a furnace?
Like turns off the system until, I mean, some certain temperature point.
Yeah, in case your furnace got too hot. So if your furnace overheats, let's shut it down electrically. So a limit switch is mounted on the furnace, and if the furnace overheats, just kill power the gas valve. So they'll mount that limit switch to where it's sensing the temperature near the heat exchanger. The heat exchanger is where the combustion's taking place. So right underneath the burner here, I have a limit switch. There's
They
another
have those on dryers.
They have them on dryers too, good.
Yeah, ovens. Right.
Ovens too. Ovens have limit switches on them. Anything that like gas cooking or even electric, this is a good safety device in case it overheats. So these limit switches, they'll rate them by temperature. So they'll say, okay, well, this limit trips at 180 degrees. So what you're going to want to do if the limit is tripping, you got to find out, is it a bad limit or is the limit switch doing its job? Because sometimes the limit fails and sometimes the furnace overheats. So one of the easiest ways to troubleshoot these limits is if you're losing voltage on the limit, all of a sudden you're reading 24 volts on it. Take out one of the mounting screws and put your thermometer in that hole for the mounting screw. If that limit says it's supposed to trip at 180 and it's tripping at 140, you have a bad limit switch because it's not supposed to open until 180. If you put your thermometer next to it and it is getting up to 180, then the limit is not bad. The limit switch is doing its job. The furnace is getting too hot. What is the number one reason why a furnace would get too hot?
Clogged filters.
Good job. Dirty filters. What do they mean by temperature rise on these? That's how much the furnace is going to heat up there. So what you're going to want to do is find the temperature rise on the furnace. So on this one, it says 30 to 60 degrees. All right, so different. So let's say the return air or room air is at 70. What we're going to do for our supply air range is we're going to add that temperature rise to our return air. So if I do 70 plus 30, on the low end, I want to see 100 degrees supply air if the room is at 70. On the high end, I do the 70 plus the 60. And on this particular furnace, if the room is at 70, on the high end, the supply air should be up around 130. So if you had dirty air filters and the room was at 70, is your supply air going to be closer to 100 or closer to 130 if you had dirty air filters?
The clogged return air, closer to 130.
It'd be 130 because you have less air going across the furnace because of the dirty air filter. That being that we have less air volume, that furnace is going to heat the hell out of that air that's going across it. And we're going to have really hot supply air. So if you had dirty air filters, or if you had like undersized ductwork, or if people go around and they start closing off registers in their house, they can make it where the furnace overheats. And then if the furnace overheats, you can end up tripping a limit switch. So on these furnaces, they give you a temperature rise on the furnace. And this is something that you want to check out anytime you do a maintenance. Measure the return air, find your temperature rise on it, and then make sure your supply air is within range. If you're too cold, that means you have either too much airflow or you're under firing. So maybe you have low gas pressure. Most likely it's probably something with airflow, but if it's too cool, it could be low airflow, high airflow, or you're under firing on that gas valve. And then if the air is too hot blowing out, you have low airflow going through the furnace. If your air is blowing out too hot, or your gas valve could potentially be overfiring. Normally the gas valve is pretty reliable. So when your supply air is not in range, most likely it's something to do with the airflow across that furnace. So in a big house, like let's say you had 8 vents in that house, you shouldn't be closing off like 4 of those vents. If you close off half the vents, you're not rejecting heat out of the furnace. The furnace is going to overheat and it's going to go off on limit. Other than the furnace shutting down electrically, is there a problem with the furnace running too hot? So other than it shutting down electrically, is there a problem with the furnace running too hot? Yes, there is. The heat exchanger is where the combustion takes place. So these flames, they shoot into this heat exchanger. So the more you heat up the metal, or the hotter the furnace is running, the more that metal's going to expand. And then when the furnace shuts down, it's going to contract back. That expansion and contraction is eventually what's going to crack that heat exchanger. You guys can hear the heat exchanger when it's expanding sometimes. So sometimes you guys have lived in a house, you kick on the furnace, and then you hear this like ping, ping, pong, like these weird metal sounds, like almost like water's hitting metal. It's got a weird sound to it. That's the metal expanding in that heat exchanger. Or when it's cooling down, that's the metal contracting back. The problem is if you get a crack in your heat exchanger, now you're dumping carbon monoxide into the house. This heat exchanger should be sealed so that all the flue gas goes up the flue pipe. If there's a crack in it, we're going to blow room air across that heat exchanger. So if there's a crack in the heat exchanger, if there's a crack in this heat exchanger here, now when the blower kicks on, room air is going to make it into the heat exchanger. That's going to make your flame move around. But what's worse is the carbon monoxide that's in the heat exchanger is going to leak out into your ductwork or leak out in your furnace, which then makes it to your ductwork. And now you're dumping carbon monoxide into the house every time you run the furnace. So we definitely do not want a cracked heat exchanger, because then you're going to go nighty-night and you're not going to wake up again. So any old furnace, you got to check the heat exchanger. If you don't check it, who's going to? You know, that's the way I always looked at it. If they have a 20-year-old furnace, I better look at the heat exchanger, because if I don't look at it, no one's going to look at it. It's not like the cable guy is going to be like, oh, hey, let me check out your heat exchanger. You know, no one's even thinking to look at it other than an HVAC tech. If it is an older unit and it's kind of questionable, sell them some fire alarm and carbon monoxide detectors, and then put the carbon monoxide detectors up near their supply registers. If that thing starts beeping, there may be a crack in that exchanger that you're just not seeing. They're not easy to find, the cracks in the heat exchanger. What I do is I buy this product called Heat, HEAT, and then I fire up the furnace and I spray that product in the blower airstream. I cannot spray it on the motor side. If I spray it on the motor side, I'm going to short out the motor. I spray it on the opposite side of the blower motor. So the scroll cage picks up this product, it blows it across the heat exchanger. If there's a crack in the heat exchanger, that product will make it in there and the flame will change colors. So instead of the flame being orange, blue with orange tips, that blue flame is going to turn bright yellow. So if all of a sudden I spray my product in the blower airstream and the furnace flame turns yellow, there's a crack. Now I need to condemn that furnace. So I'm going to shut off the gas and I'm going to unhook the W wire so the customer cannot use that furnace. That product is really hard to find. Johnstone sells it. I'll look around. I'll find you guys what the bottle looks like. For me, it's the easiest way to check a heat exchanger, Because if you don't use that, how else are you gonna find the crack? It's hard to tear it apart to look at it. Sending a camera down each tube, that's a nightmare trying to find the crack, especially if it's a hairline crack that only opens up when it's hot. Because you can't send the camera in there when the flame's on, you're gonna burn your camera. So when you go to check the tubes on the heat exchanger, the camera's, it's all right. But I much prefer this product called Heat. Because you just spray it in there, you look at the flame, and if it changes colors, you have a crack. Yeah, Google sucks now as far as looking up stuff. I agree. It's definitely gotten worse. All right, so that limit switch is a safety type device. We have rollout switches in case the flame rolls out. Any of these safeties are normally closed, and then they're going to open when there's a problem. So bimetal, it consists of two dissimilar metals. It's brass and steel. The strips have different rates of expansion and contraction. When heated, the device warps to start, stop, or modulate electric or fluid flow. So with the bimetal, you're going to have to memorize that it's brass and steel. So the brass is going to have a faster expansion rate than the steel when heated, and it's going to have a faster contraction rate than the steel when it's cooled. So the brass and steel, when they're at 70 degrees, that bimetal is just vertical there. And then when they heated up the bimetal up to 75, the brass expanded at a faster rate than the steel, and the bimetal warped to the right. Then when they cooled the bimetal down to 65, the brass contracted at a faster rate than the steel, and it warped to the left. So we can use that bimetal to do a number of things. So one, we could just put a switch on it. So on this one, when it was heated up, it warped to the right and the switch opened. And then when we cooled off the bimetal, the brass contracted, it warped back to the left, and the switch closed. So inside some of your thermostats, even in the shop, you guys have bimetal in that thermostat. So some of the real cheap ones we have, they just have bimetal in there. And then when you heat up that bimetal, it's going to warp one way or another. They can mount a mercury bulb on the top. So when the bimetal tilts one way, it calls for cooling. When the bimetal tilts the other way, it's going to call for heating. So that bimetal is used a lot to sense room temperature and also temperature of components too. So when they lengthen it, they'll just coil it up. They may do like a worm style with it. So there's different ways they can lengthen that bimetal so they could get some more movement. So like on this one, some of the thermostats will use letter A, and then they'll mount a mercury bulb up here on the top. And the mercury is our switch. So when it warps one way, it'll call for heating. When it warps the other way, it's going to call for cooling. So if you see a mercury bulb thermostat, mercury is a switch. Bimetal is what's sensing the room temp. So they'll show a picture of the rod and tube in a minute. The rod and tube type of bimetal control, you have an outer tube with a high expansion rate, that's your brass, and an internal rod with a low expansion rate, that's your steel. And then any switch should be a snap disc where it's quick to open and quick to close. So on your water heater, on some of your water heaters for the gas valve, they're using a rod and tube. So the tube is brass. And right now the hot water heaters is the tank is warm and the hot water is up to the temp we wanted at. So once the water is hot, this brass tube expanded, and due to this little pivot off of the steel rod, we shut off gas flow going to the burner. And then once the water in the water heater cools down, it's going to cool down the brass. The brass is going to contract a little bit. When it contracts a little bit, it's going to push over on that pivot. When it pushes over on that pivot, it opens up the gas valve so that we have gas flow to the burner. In your overloads and in your limit switches and rollout switches, you guys have a snap disc. So this would be your brass and steel, and we want it to snap open and snap closed. So like on your overloads, if you pull excessive amperage through the bimetal, that excessive amperage is going to heat up the bimetal and it's going to cause it to warp and it's going to snap open. When they say snap open and snap closed, they just want it real fast. So when those contacts close, boom, they close extremely fast. Same thing when they open. Because if they're slow to open and close, we're going to have arcing in the contacts, and that's going to burn out our contacts prematurely. So any sort of switch should have a snap action to it. So fluid by expansion is still used a lot. Fluid inside a closed container expands and contracts as the temperature changes. This expansion and contraction is converted to motion. A thin, flexible diaphragm facilitates the motion. We have a bulb filled with a volatile fluid that connects to the diaphragm by means of a transmission tube. The volatile fluid is refrigerant. They could use mercury, but they haven't used mercury since the 80s. So the odds of you coming across a mercury-filled fluid control valve or fluid controlled switch is going to be pretty slim to none. You may still come across some of the mercury controls, but they're not real popular. And they're kind of easy to identify, the mercury filled ones. So these were used on furnaces. It was filled with mercury, and it is proved the pilot flame was lit. So once you heated up the mercury expanded, closed a set of contacts, telling the furnace that the pilot was lit. So if you had a really old furnace, you could still buy these parts, but they're super expensive. Just because it's such a rare part now, they jacked up the price because these used to be like $20, and now they've just, you know, gone like 10 times the amount of what it should be.
Exactly the same thermostats in the ovens.
What's that?
Exactly the same thermostats in the ovens.
Yeah, you'll see those in ovens too, some of the mercury filled ones. And it's just to prove your pilot was lit on there. All right, we have some partially filled partially filled bulbs provide accurate control. So that they don't want to fill it 100% full of liquid because we need some room for expansion in there. And then bellows are used when more movement is needed. So we have a sensing bulb filled with refrigerant. And as we heat this refrigerant, it's gonna, the pressure is gonna go up. And when the pressure goes up, it's gonna cause this diaphragm to warp upwards. So we use this on thermostats still. If you have a thermostat like on your household refrigerator, so this thermostat is a fluid filled control. Same with this one. So some of these are for defrost. This is bimetal. This is fluid filled. And then we also see it a little bit in commercial refrigeration, where they use the same type of fluid filled controls. So this would be off a commercial unit, and it looks pretty much like your residential one. Now, in that sensing bulb, that wire, it's actually it's not a wire, it's a tube, and it's filled with refrigerant. So if you cut off that sensing bulb, you ruin that control. So right now the refrigerator's at 35 degrees. So the pressure in this sensing bulb is only at 30 PSI. That's not enough pressure to warp the diaphragm upwards and cause this switch to close. Now the refrigerator is up to 45 degrees. So we heated the sensing bulb up to 45. That's going to give us a pressure of 40 PSI. That's enough pressure now to warp that diaphragm upwards. And now we're calling for cooling. So if you cut that sensing bulb, you're going to vent out the refrigerant that's in the sensing bulb, and there's no way to refill it. You can't put it back in there. So if you cut off the sensing bulb, you ruin that control. Oh, don't worry if you join late and didn't know there was class, you're right. This is recorded, I'll put it online. So any of these recordings, I'll put them on Canvas like the next day after the class is over. when you guys go to replace these thermostats, don't reinvent the wheel. I always tell myself that acronym, KISS, keep it simple, stupid. So when you're out there, you don't have to call yourself the last S. You could just say KIS, keep it simple. I like to talk down to myself, so I always say they keep it simple, stupid. When you guys go out there, keep it simple. So if you have an old thermostat that was model number 701, go with a 701 replacement. And then wherever the sensing bulb was, put the sensing bulb back in the same spot. So if the old thermostat had the sensing bulb in the middle of the evaporator fans, put the new sensing bulb in the middle of the evaporator fans. Don't pick a new location for it. If you do, you're going to have problems. So when you go to replace these thermostats, try and go with the same model number. That way you have the right cut-in temperature on it. If you go with a different one, a different model, you are going to have to sit there and play with it. So once you put it in, you're going to have to put your thermometer inside the refrigerator and really watch that thing to see where it's cycling on and cycling back off at. So whenever you go to replace these, wherever that sensing bulb was mounted, you mount the new one in the same location. And if they set the old one on number 4, set the new one on number 4. It obviously worked for the last 10 years. So put the sensing bulb in the same spot, set it at the same number, and then put your thermometer in there and see if it's working the way it should. Now with the sensing bulb, or with the diaphragm, we're limited on how much movement we can get off that diaphragm. That diaphragm is just a thin metal disc. So if I want the control to cover a big range, a diaphragm type control is not the best way to do it. What the manufacturer will do is they'll have a control with bellows. So inside of the control, instead of it being a thin metal disc that's going to warp up, they have something that looks like an accordion. And now when we increase the pressure on it, this thing has a lot of movement. It could really expand a lot. And then if we decrease the pressure, it could really constrict down quite a bit there. So if you look at like a high pressure switch, let's do it to oil. All right, so on the dual, you have a high pressure and a low pressure next to each other. When we look at the bottom here, that's where the diaphragm or the bellows would be. So when you look at the low pressure side, this metal part is not very tall. Odds are they have a diaphragm in this one. Just that thin metal disc warping upwards. The high pressure range, they're trying to go from 100 PSI up to 500 PSI. So that diaphragm is not going to cover that big of a range. So inside of here, they'll put bellows in here so it covers a bigger range. Honestly, you could probably care less whether it had a diaphragm or bellows. All you care is, does the control work? So if they have it set to cut out at 250, that switch should open up at 250. Just know that there are different ways that they can use that they can convert that fluid expansion to a usable motion. One way is the diaphragm, another way is the bellows. Like I said, I don't care what they put in the control as long as it works. If you're ever messing around with a screwdriver at the bottom of that control, don't puncture the diaphragm or the bellows. So you can actually see the bellows sometimes. Make sure you don't ever stick a screwdriver through it, because now you're going to have a massive leak. Or if it was a thermostat with bellows, you ruin the thermostat. Questions on the diaphragm or the bellows or the fluid filled controls? So don't cut off the sensing bulb. You ruin the control. Off your gauges or in your gauges, you guys have a board-on tube. That's a thin brass tube that's going to expand under pressure. So instead of it going to a sensing bulb, if this was your manifold gauges, this would be your blue hose or your red hose coming off of that gauge set. And then when you increase the pressure, that brass tube inside straightens. When it straightens, it's going to move this little linkage, and then that's going to move your needle. So it's they're pretty sensitive. If you beat these around, they'll definitely go out of calibration. So on your gauges, you can recalibrate them. So if you want to calibrate a set of gauges, you're going to open them up to atmosphere. Oh, I didn't copy. Anyways, you're going to open up the hoses, the bottom of the manifold, to atmosphere. And then there's a little set screw that you can recalibrate these to 0. Like the one they're showing in the picture, this needle's not right on 0. This thing needs to be recalibrated. So you can recalibrate mechanical gauges. And then these nice digital gauges, they have a little button on them that you can recalibrate them. So you'd have to open them up to the atmosphere, so it's sensing atmospheric pressure, and then you zero it out at atmospheric pressure. If you're in the 122 course, start playing around with these nicer gauges. They do everything for you. The superheat subcooling, they have a micron gauge built into them. So we have these at school. Definitely learn how to do all your superheat subcooling on a mechanical set, but then you can also get a digital set, and it helps out a lot because it does all your calculations for you. The price of them is pretty expensive though. So when you guys get started in the field, it's a lot cheaper to buy a mechanical set of gauges than it is a digital set of gauges. This is like your meter where you want to buy a good name brand. So Yellow Jacket, Field Piece, JB, the Just Better. Ritchie, buy a good name brand on your gauges. If it's something like this Pittsburgh one, this is garbage. This Harbor Freight one, they might last for a while, but they're not going to last as long as the Yellow Jacket. So when you buy your gauges, I'd be cautious about buying the real cheap ones. They're just not going to last. And like these ones are not even 410A rated. These are for 134A. So it's more for like cars. It doesn't even have the 410A rating on them. All right, the thermocouple, this consists of two dissimilar metals joined end to end, has a hot junction and a cold junction. The two metals are not brass and steel. The two metals are iron and Constantine on the thermocouple. When these metals are connected, they form an electrical circuit, and current will flow when heat is applied to one end of the device. So when we apply heat to the hot junction, we're going to get a small amount of current flow through those dissimilar metals. These were used to detect the pilot light flame. They still are used. So on gas water heaters, a lot of gas water heaters still have thermocouples. And then we could have multiple thermocouples can be wired in series with each other, and they call this a thermopile. So on your gas valve, if you have a standing pilot, that means the pilot is on all the time. If you have a standing pilot, we have to prove to the gas valve the pilot is on. One popular way was using a thermocouple. So when I heat up this thermocouple, it's going to generate between 20 and 30 millivolts. $1,000 millivolts equals 1 volt. So you're talking very low voltage if this thing is only 30 millivolts. All it's doing is powering up the pilot portion of the gas valve. So there's a little pilot solenoid, and that thing is going to operate off of 30 millivolts. So some of you guys have lit water heaters, and some of you guys have lit furnaces, and then others of you have not done it yet. So it depends on the gas valve. So some of these have a red button we're going to have to push down. This one's a goofy knob. So it has off, pilot, and on. So when you guys go to light a water heater, the first thing you need to do is turn the gas valve off. You have to make sure there's no residual gas in that water heater. If you pull the cover to get down by the pilot and it smells like gas, don't light it. You're going to have a big delayed ignition. That flame's going to come out after you. So the first thing you want to do is turn it off. Let the gas dissipate out of the furnace or out of the water heater. The next step is you're going to have to put the gas valve in the pilot position. So you're going to have to spin this knob, and then you're going to have to push the knob down and hold it down in the pilot position. What you're doing when you're holding it down is you're forcing the gas valve open. So you're forcing it so gas can come out that pilot line. And then you're going to get in there with your lighter and you're going to light the pilot. And then once you light the pilot, you still have to hold that button down for 30 seconds. What am I waiting for in that 30 seconds? Because the pilot's already lit. Why do I need to wait 30 seconds before I let loose of that button? I'm waiting for something to get hot. What am I waiting for to get hot? It's your thermocouple. Because that thermocouple is not going to put out 30 millivolts if it's cold. So once you get in there and you light the pilot, you should have a nice pilot flame on the thermocouple. Well, that thermocouple is going to take, 30 seconds for it to get smoking hot. So if you just push down the button on pilot, light the pilot, and then let go of the gas valve, that thermocouple is not hot enough to energize the pilot coil on that gas valve. So the flame's going to go out right away again. So you have to hold the pilot open for 30 seconds. After 30 seconds, you can let loose of it, and the pilot will stay on. Then you have to switch that little knob to on the gas valve. So when you go to light a water heater, turn the gas off. Make sure that there's no residual gas in that water heater. You can't smell it. Then you're going to put the gas valve in the pilot position, have your lighter ready, push down on the button on the gas valve, reach in there and light the pilot. The pilot's going to light, and now you're waiting 30 seconds to heat up this thermocouple. After 30 seconds, that thermocouple will keep the pilot coil of the gas valve energized. So it's powering up the pilot portion of that gas valve. Now, as long as that pilot is lit, you're going to keep producing the 30 millivolts. As long as you have 30 millivolts to the coil, the pilot portion of the valve stays open. Some of you guys have lived in places with a wall furnace. I know California is trying to get rid of these, but the nice thing about them is, there's a few nice things. One, they're super cheap. Look at the price of these. They're dirt cheap. And then two, when the power goes out, you still have heat. The whole wall furnace is going to operate off of a pilot generator. A pilot generator is a thermopile, which is a bunch of thermocouples ganged together. It's hard to draw on this with the mouse. All right, so this would be my little my pilot generator. AKA thermopile. Looks similar to a thermocouple. It's just a bunch of thermocouples ganged together. And then on that wall furnace, they're going to wire that thermocouple, or sorry, that pilot generator into a gas valve. And on that gas valve, we'll have a connection called PV. We'll have a connection called MV. And we'll have another one that's MV/PV. That's just common on the valve. So when they go to wire these, they'll take one side of that pilot generator. They'll go to common. They'll take the other side and they'll go to the pilot valve. So as long as that flame is heating up the thermocouple, or sorry, thermopile, we're going to produce between 500 and 750 millivolts. So also less than 1 volt. Because 1,000 millivolts is 1 volt. So once you light the pilot, this thermopile is going to produce that 500 millivolts. That 500 millivolts is going to power up the pilot portion of the gas valve. So once you held down your button for 30 seconds, you heated up the thermopile enough to where it produced 0.5 volt. That pilot portion of the valve operates off a 0.5 volt. Then what they'll do, so as long as we have the thermopile wired into the pilot portion of the valve, the pilot portion of the valve is going to stay energized as long as the pilot's lit. So now what they're going to do is they want to wire in a wall thermostat or a room thermostat. So they're going to come off the pilot portion. They're going to go over to a room thermostat and then to the main. So now when the room gets cool, we're going to send 500 millivolts to the main. Main's going to open. We're going to send gas across the pilot, and that's going to light the main burner. Then once the room gets warm, the thermostat opens, killing power to the main, but it does not kill power to the pilot. So if any of you guys lived in an apartment that has a wall furnace, the pilot is on 365 days of the year. They have newer ones that are intermittent ignition, but most all the old ones, you got a standing pilot. So like the apartments that I've lived in that had a standing pilot on the wall furnace, that thing's putting off heat all summer. It's 1,000 BTUs per hour. It's not a lot, but it's definitely putting off some heat. So any apartment I've lived in that had a standing pilot on the wall furnace, I'm going to kill the gas come summertime, come spring. I'm shutting off the gas. And then in the fall, I'm going to go ahead and I'm going to relight that pilot. If you're doing that, do not tell your apartment maintenance, your apartment manager you're doing that. They don't want you touching the equipment. So if you're a resident in an apartment complex, it's a big no-no for you to touch the equipment. But there's no way in hell I'm going to live in a place with a standing pilot on all summer long. It's just putting off heat that the air conditioner is going to have to absorb. So personally, I'll go shut off the gas, and then come wintertime, I'll go in and relight the pilot. Cool thing is when the power goes out, all the power from the furnace is coming from the pilot generator. Hence the name. The pilot is generating the electricity for that furnace. So the cool thing is when the power goes out, you still have heat. All your neighbors that have central heat or a heat pump, or they have baseboard heating, once the power goes out, they have no heat. So there is a definite advantage of having a wall furnace is when the power goes out. Questions about the thermocouple or the thermopile? So what we'll do in lab I'll find some thermocouples and we'll put a flame to them. And then we'll measure the millivolts coming off of it. So if it's a thermocouple and we heat it up, we should get about 30 millivolts off of it. If it's a thermopile, aka a pilot generator, and we heat it up, we should get about 500 millivolts off of it. All right, that's where I wrapped it up with the early group. For lab, I do apologize. I was sick the week before spring break. I got the flu. We had talked about it the week before spring break on Tuesday that we were going to do lab 9. So lab 9's gonna have a refresher. Lab 9's gonna have 2 parts. Part 1 is just you drawing out this pictorial diagram. So you're gonna take your ladder and transfer it to the pictorial. And then when you guys come into the lab on Thursday, there's gonna be 2 portions of lab 9 to wire up. So one of them, we're gonna wire the stop start push button without a holding circuit. So that means the whole time that you want the motor to run, you got to push the start button. And then we're going to wire it also with a holding circuit. So once we put in the holding circuit and you push start, the motor is going to stay on until you push stop. So we're going to wire the stop start push button 2 ways. One with a holding circuit, one without the holding circuit. And then also, like I said at the beginning of class, I put your Unit 12 exam online. I gave you a bubble sheet to fill out, and then you can resubmit this online. So just fill out the bubble sheet, take a picture of it, and then upload it. If that's inconvenient, you can always just give me the bubble sheet on a Thursday night.